Dear students, welcome to our fluid mechanics class. So, up to last class, we discussed fluid kinematics. We will see problems also in fluid kinematics. So, from today's class, we will discuss fluid dynamics. So, this is the second chapter in the unit 2. Okay. So, fluid dynamics is very, very important. So, why? Because next semester you having you are having a fluid mechanics lab. Okay, so in that fluid mechanics lab there are around 12 experiments is there. So out of the 12 experiments, majority of the experiments are related with the fluid dynamics only. Okay, especially Bernoulli's theorem. Okay, so that theorem today we will discuss how to derive the Bernoulli's equation and what are the significance of the Bernoulli's equation. Okay, so let us go to our class. So first introduction about fluid dynamics. So what is meant by fluid dynamics? So what is the difference between fluid kinematics and dynamics? So fluid kinematics, the force causing motion. Okay, we didn't consider the force causing motion, but fluid dynamics, that force also we have to consider in the fluid motion. Okay, so in fluid dynamics, the forces are considered for the analysis of fluid motion. The dynamic behavior of the fluid flow is analyzed by the Newton's second law of motion. Okay, Newton's second law of motion. So what is Newton's second law of motion? So force is equal to mass into acceleration. Okay, force is equal to mass into acceleration. So fluid dynamics is we have to relate with the Newton's second law of the motion. Okay, so the fluid is incompressible and non-viscous. Okay, so we are considering that fluid is incompressible fluid and a non-viscous fluid. Okay, so this chapter is applicable for incompressible and non-viscous fluid. We know that the best example for the incompressible fluid is water. Okay, so next important equation is Euler's equation. Okay, as I told already, Bernoulli's equation. Okay, Bernoulli's is the scientist. Okay, so Bernoulli's equation is derived. Bernoulli's equation is derived from the Euler's equation only. Okay, so what is by Euler's equation? So the Euler's equation for steady flow of an ideal fluid along a streamline, okay, is a relation between the velocity, pressure and density of a moving fluid. So what is Euler's equation dealing? Okay, so Euler's equation dealing velocity, pressure, density. Okay, these three important parameters at a time. Okay, they're dealing velocity of the fluid, pressure in the fluid and the density in the fluid. Okay, so it is based on the Newton's second law of motion. The integration of the equation, that means the integration of the Euler's equation gives the Bernoulli's equation in the form of energy per unit weight of the flowing fluid. So here we are calculating the energy, how much pressure energy, how much velocity energy and datum energy. Okay, so this also called head. Okay, so these are all the things we can easily find using the Bernoulli's equation. Okay, so before going to the Bernoulli's equation, first we will derive the Euler's equation, because once you derive the Euler's equation, Bernoulli's equation is very simple. Just integrate the Euler's equation. Okay, just integrate the Euler's equation. We can get the Bernoulli's equation easily. Okay, so now we will move to the Euler's equation. So what are the assumptions? So while deriving any type of derivation, we must first consider some of the assumptions. Based on that only we are deriving, okay, the something. Okay, so it is based on the following assumption. So Euler's equation is derived based on the following assumption. The first assumption, the fluid is non-viscous. Okay, the fluid is non-viscous. That is, the frictional loss are zero. So, but practically it is not possible. Okay, so if you take water, somewhat very little bit viscous is there. So if you take honey or a castor oil or some other oil, means the fluid viscosity is more. So we can't tell a fluid having 100% non-viscous. Okay, but in our assumption, we assume that the fluid is non-viscous. Okay, so for a assume that water is a non-viscous fluid. So next, the fluid is homogeneous and incompressible. What is mean by homogeneous? The property of the homogeneous means what? That means the property of the each fluid particles is or fluid molecules is same everywhere. Okay, everywhere it is same. That is called a homogeneous and incompressible. That means the density of the fluid is constant. This we already discussed in the fluid kinematics in the type of fluid flow. Okay, so the fluid density is constant. That is called incompressible flow. So next, third one, the flow is continuous. The flow is continuous, steady, and along the streamline. Along the streamline. Okay. So streamline is a line. So the flow is going along the streamline. So it consider it is an axis. So it will flow along the axis. Also, the flow is steady flow. Okay. So next, the velocity of the flow is uniform over the section. Okay, the velocity of the flow. So this equation not applicable for the bearing cross section pipes. Okay, so if you take a bearing cross section, the velocity is keep on changing. If the cross section of the one end of the pipe is very small, velocity is high. So other end, the diameter, the cross section is more, means the velocity is slow. Okay, so here for uniform cross section pipe we have to use this one. Okay, so next, no energy or force except gravity and pressure force is involved in the flow. Okay, so no energy or force. So only there are only two types of force only acting. One is gravity force. Okay, gravity force. So how gravity force occurs? So gravity force is occurs always in the downward direction. In the downward direction. And the pressure force. Okay, so we know that in case of fluid is flowing means somewhat pressure is occurs. Okay, that pressure force is involved in the flow. So this 5 important assumptions is necessary while deriving the Euler's equation. So keep it in your mind. Okay, and now we will start the Euler's equation, derivation for the Euler's equation. So this is equation. This is equation of motion in which the forces due to gravity and pressure are taken into consideration. Okay, as I already told, only two forces only we are considering. One is gravity force and the pressure force. Okay, so this is derived by considering the motion of fluid element along a streamline. Along a streamline. So consider this figure 6.1. Okay, so you can see here this is the line, streamline. So yes, okay, S is nothing but streamline. This is the line. Okay, consider a streamline in which flow is taking place in x direction as shown in figure 6.1. So consider a cylindrical element of cross section. So here we are taken a cylindrical fluid element, cylindrical shape. Okay, the cross section area is dA. So from that cylindrical element we taken a small cross section area. So that cross section area is dA, and the length is ds. Okay, the cross section area is dA and the length is ds. Full stop. The forces acting on the cylindrical elements are, the forces acting on the cylindrical elements are. So what are the forces acting? So there are three major forces are acting. Three major force. Okay. So first force is pressure force. First force is pressure force. So here, listen. Here I am not taking pressure. Okay, I am not considering pressure. I am considering pressure force. Okay, pressure force. How to calculate pressure force? See, pressure is equal to, what is the formula for pressure? Pressure is equal to pressure force divided by area. Like stress. So what is by stress? Load by area. That means internal resisting force divided by unit area. Likewise here, I am calculating pressure. Okay. So if I want to, that load means what I have to do? Stress into area. Okay, stress into area, nothing but force. So same way here, we need a force means we have to multiply pressure into area. Okay, we have to multiply pressure into area. So pressure multiplied by the area, which gives the pressure force. Okay, in the direction of the flow. So here I am considering only force, not pressure. Okay, keep it in your mind. Okay, so the first force is pressure force. So this is small p is nothing but the pressure. Okay, multiplied by the area, which gives the pressure force in the direction of flow. First one. Next, second one. Second one is also a pressure force, but it acting in opposite direction as per Newton's third law. What is Newton's third law? Every force, okay, every force having a equivalent opposite force. Okay, so every reaction having same equivalent opposite reaction. Okay, so same way here, pressure force. So you consider in this cylindrical element, okay, the length is ds, okay, and this area is dA. So now you can consider this is the pressure force acting from downward to upward, P into dA. So next, the opposite force is nothing but the opposite pressure force. So what is that opposite pressure force? This opposite pressure force is nothing but already one pressure is there plus the pressure acting in this element. Summation of the pressure acting in this element plus external pressure. So what is the pressure acting in this element, small element? So that is called dou P divided by dou S into ds. Dou P divided by dou S into ds. Okay. So these are all the total force. Okay. So external pressure force plus internal, that means inside the cylinder. Okay. That pressure. Okay. So these are all the total pressure multiplied by the dA. That means area. So this pressure into this area gives the pressure force. But it's acting as per Newton's third law, opposite direction. Okay. So next, third one. So okay, pressure force in x direction and y direction we calculated. Okay, sorry, y direction and minus y direction. Next, there will be a weight of the fluid element is there. So how to calculate this weight? Okay, so please listen. We must calculate the weight. So what is the formula? Rho into G. Rho into G. So rho into G multiplied by the volume. Multiplied by the volume. Volume of this element. Okay. Rho G dA ds is the weight of the element. We already seen weight formula, specific weight formula in the first unit properties of the fluid. Okay, so rho into G into V, rho into G into V, which gives the weight of the element. Okay, so rho G is the specific weight multiplied by the volume means we can easily get the weight of the element. Okay, now so now let theta is the angle between the direction of the flow and the line of action of the weight of the element. So now you can see the fluid element is not a perfect vertical. So it was tilt into some angle. Okay, so it is an inclined element. So how much inclination? The angle of inclination is theta. Okay, so this is the direction of the pressure force acting, and this is the rho g dA into ds is the weight of the element. It acting pure vertical direction. Pure vertical direction. So you can see here. Take down this triangle. Okay, so this theta. This is the theta value, and this is the ds length. Okay. So now the summation of the total force. The summation of the total force. So now this force is acting from downward to upward. Okay. Now this force is acting from upward to downward. See the arrow. Okay. And also this gravity force. This gravity force. That means the weight is also acting from upward to downward. So two forces. This force and this force is acting upward to downward, and this force is acting from downward to upward. So I am taking this as positive and these two are negative. Okay, now you can see here the resultant force on the fluid element in the direction of S must be equal to the mass of the fluid element, the mass of the fluid element into acceleration in the direction S. So the mass into acceleration is nothing but the Newton's second law, mass into acceleration. So now I am writing the whole forces. Okay, the summation of all the forces. So P into dA, it is acting from downward to upward, minus P plus dou P divided by dou S into ds into dA. This force is the opposite force acting downward, minus rho G dA ds into cos theta. What is this cos theta? So now you can see here, this is pure vertical. So this force along this pressure force. Okay, so this gravity force, this weight along this gravitational force, this weight is along the pressure force. We have to calculate along the pressure force. What to do? So this is adjacent side. This is adjacent side. This is your hypotenuse. So rho g dA ds cos theta means this line will merge into this line. Okay, so this will acting downward. Okay, so simply telling means we are convert the vertical force into that inclined one, vertical weight into the inclined one along with the pressure force. Okay, so we have to use this angle is theta, so we have to use cos theta. Okay, so which is equal to this whole equation, which is equal to mass into acceleration. So this is your mass, rho into dA ds, density into volume. Okay, so what is the density formula? Mass per volume. We already seen in the first unit, properties of the fluids. So density is equal to mass per volume. We need only mass means density into volume. Okay, into AS. Okay, A is nothing but acceleration in the direction S. A means acceleration and S is the direction. Now, what is meant by acceleration? Where A is the acceleration in the direction of S. Now, what is meant by acceleration? So, acceleration is nothing but velocity with respect to time. Velocity of the fluid with respect to time. So here we are taking a small velocity. So dou v divided by dou t, where v is a function of, where b, velocity is a function of s and t. Okay. So what is s? S is the length. That means along the streamline. ds is the length of the element. So velocity is the function of s and time. Okay. So now I am rewriting this equation like this. Dou v divided by dou s. Dou v divided by dou s into ds divided by dou t. Okay. So this velocity along the direction of s and ds divided by dt plus dou v divided by dou t, this equation. I am writing this equation here. Okay. So since velocity is a function of s and t, so we have to include that s and t terms. Okay. So dou v divided by dou s into ds divided by dt plus this dv divided by dt. This acceleration acceleration in the direction of x. Okay. So which is equal to v into dv divided by ds. How this v will come? See, v is nothing but distance divided by time. That means velocity, distance divided by time. Like our kilometer per hour in your bike or car, we are traveling some distance. So how much time it will take, and means that is the velocity. So distance divided by time is nothing but velocity. So here you can see ds divided by dt is there. So v. Next thing is dou v divided by dou s. Okay, so dou v divided by dou s plus dv divided by dt. Okay, dv divided by dt. So for in this case of flow is steady. See, we already seen velocity will not change with respect to time in case of steady flow in the fluid kinematics. Okay, velocity will not change with respect to time. So dou v divided by dou t, which is equal to 0. So just understand how this equation came. So ds divided by dt is nothing but the velocity. So put b. That's all. Next, dou v divided by dou s. Again you write here plus dou v divided by dou t. Okay, this is already available. Okay, so now the velocity is steady means this dou v divided by dou t, which is equal to 0. So therefore as is equal to v into dou v divided by dou s. Okay, so this as is equal to dou v into dou v divided by dou s. So this is the acceleration in the direction of s. Okay, so substitute. So this term will get 0. Dou v divided by dou t will get 0 because the flow is steady means dou v divided by dou t is 0. So what is the balance thing? As is equal to v into dou v divided by dou s. This is the balance term. So now substitute this equation. As is equal to v into dou v divided by dou s in this first equation. Okay, in this portion. So substituting the value of as in the equation and simplifying the equation, we get minus dou p divided by dou s ds dA minus rho g dA ds cos theta. Okay, equal to rho dA ds into v dv divided by ds. So now you can see here. Okay, so this is the equation. So I can rewrite this equation like this. Okay. How this equation came means, how minus dou p divided by dou s ds dA came means, now you can see here plus p into dA is there, plus value. Now here one p is there, outside one dA is there. So this dA multiplied with this p means, and outside of the bracket one minus is there. Okay, so minus p into dA. So here plus P into dA and here minus P into dA. Okay, so it gets cancelled. So we can rewrite that equation like this. So substitute AS is equal to B into dB divided by ds. So now I divide the common terms. That means rho into ds dA. So what are the balance thing? Minus dou P divided by dou S. Next to minus G into cos theta. Okay, because this rho ds dA get cancelled. And here also rho dA ds cancelled. Balance thing is B d dou B divided by dou S. Okay. Or again I am simplifying. So dou P divided by rho ds. So this value I put plus. Okay. Plus G into cos theta. These two terms comes into cos theta. Okay. So if this 2's are goes to right hand side. Okay, other side of the equation equal. Okay, so this minus value goes to this side means get plus value. So dou P divided by rho into ds plus G into cos theta plus B into dou V divided by dou S equal to 0. So this is the final equation we got. Okay, so now we have to put cos theta. Cos theta is equal to dou S divided by ds. So you can see in this equation the vertical height is ds and this inclined portion length is, that means length of the cylinder is ds. So now cos theta equal to ds divided by ds. Okay, sorry, ds divided by ds, dz divided by ds. So from this equation substitute cos theta in this equation. So I taken rho outside. So 1 by rho dou P divided by dou S plus G into in the place of cos theta you write ds divided by ds. Okay, here plus V into dV divided by ds, which is equal to 0. Okay, so I am rewriting the above rewriting the equation once again because here ds is the common term. You can see all these three terms, ds is the common term. When this ds goes to this side means 0 into ds, which gets 0. So now tell me what are the balance one? Dou P divided by rho plus G into ds plus V into dV. So this ds get cancelled because with the common term we can take other side of the equal which gets 0 because already 0 is there. So this is the final equation. Dou P divided by rho plus G into ds plus V into dV equal to 0. So this equation is called Euler's equation of motion. This equation is called Euler's equation of motion. So this is the Euler's equation of motion. Okay. So next we have to derive the Bernoulli's equation. What is Bernoulli's equation? So Bernoulli's equation we have to derive from the Euler's equation only. So the integration of Euler's equation is nothing but the Bernoulli's equation. Next we will see the Bernoulli's equation. So what is Bernoulli's theorem? First we will see the Bernoulli's theorem. Bernoulli's theorem states that the sum of pressure energy, kinetic energy and potential energy per unit volume of an incompressible non-viscous fluid in a streamline flow remains constant. So here pressure energy is nothing but the pressure force, how much pressure is creating in the fluid. Kinetic energy is nothing but the velocity head. Okay, how much velocity head. Next, potential energy is nothing but due to the pressure, how much what is the datum head. That means how much head is rising. Okay, head rising due to the pressure. Okay, so here we can deal with three types of energy: pressure energy, kinetic energy, potential energy. So in sometimes it's also called pressure head, kinetic head, or potential head, or also sometimes pressure head, velocity head, datum head. So there are different types of names there. Okay, anyone we can follow. Okay, so here I written pressure energy, kinetic energy, and potential energy. Okay, so the Bernoulli's equation is obtained by integrating the Euler's equation. So Bernoulli's equation is obtained by integrating the Euler's equation only. So before derive the Bernoulli's equation, here also we have to do some assumptions. Okay, the first assumption is flow is steady. So this also we did in a Euler's equation. So next, density is constant. That means this Bernoulli's equation is applicable only for incompressible fluid flow. Okay, not compressible fluid flow. For gases and that is not applicable, only incompressible fluid flow. Because gas is the compressible fluid. Next, viscosity is 0 and flow is irrotational. Okay, flow is irrotational. So these are all the basic assumptions. Based on the assumption, these assumptions only we are deriving the Bernoulli's equation. Okay. So now we can see the Bernoulli's equation from Euler's equations of the motion. So Bernoulli's equation is obtained by integrating the Euler's equation of motion as integral of dou P divided by density, that means rho, plus integration of G into ds plus integration of B into dV. B into dV is, which is equal to a constant. So here, please listen. Here it is not 0. It is a constant value. Something value will come. Okay. So if flow is incompressible, rho is constant, and so P this here integration is there, here differentiation is there. So both are cancelled. So P divided by rho, and here integration is there, here differentiation is there, get cancelled. So G into Z plus, so integral of V. What is the integral of V? It is V square by 2 equal to constant. So the final equation we got P divided by, that means pressure. P is nothing but pressure divided by rho plus G into Z plus V square divided by 2 equal to constant. Okay, so I am rewriting this equation like this. Okay, so here I am dividing the equation by G, acceleration due to gravity. Now tell me what happened. P divided by rho G plus G Z divided by G. So this G get cancelled. Okay, plus V square divided by 2G. Okay, this is the final equation. So again I am rewriting this equation like this. Just order is changed. This V square by 2G is come to second position and this Z will come to third position. So the final Bernoulli's equation is called this one. P divided by rho G plus V square divided by 2G plus Z. So this is the P divided by rho G is nothing but the pressure energy or pressure head, and V square by 2G is nothing but the kinetic energy or velocity head, and Z is nothing but potential energy or potential head or datum head. Okay, so here I written clearly. Okay, pressure energy, kinetic energy, potential energy, and pressure head, kinetic head, potential head. Okay, so this is the Bernoulli's equation. So next, applications of the Bernoulli's equation. So there are a lot of things. Okay, there are not only our civil field, even aircraft field in aerospace engineering, mechanical engineering, civil engineering, and environmental engineering. So many fields we are using Bernoulli's equation concept with this Bernoulli's theorem. Okay, So Bernoulli's equation is applied in all problems of incompressible fluid flow where energy concentration are involved. So we shall consider its application to the following measuring device. So as per your syllabus, the Bernoulli's equation is applied using this type of instruments, measuring instruments. The first one important instrument is Venturi meter. Second one is orifice meter, and the third one is pitot tube. Okay, so these are the measuring devices like our scale. So what is the purpose of we are using scale? 1 feet scale, 30 centimeter scale for measuring something. Suppose I want to know the length of the pencil or length of the paper or length of something. So how to measure? Using the scale. Okay, using the scale we can easily measure. We have to tell in terms of mm or centimeter. So likewise, suppose we have to measure how much quantity of the water is delivered. That means discharge in a pipe, or how much quantity of water is delivered in a canal. Okay, or how much quantity of water, velocity of the water flowing in a pipe or canal. Okay, so for this calculation purpose, we need some instruments. Okay, so these are all that instrument, Venturi meter, orifice meter, pitot tube. So this type of instruments is working based on the Bernoulli's theorem. Okay, so this type of instrument is designed, okay, based on the Bernoulli's theorem only. Okay, so without Bernoulli's theorem, we can't manufacture this type of instrument, measuring devices. We can't find this type of measuring devices. Okay, so these three are important measuring devices. Also from third unit second part, third unit first part, not second part, third unit first part, we have problem from this chapter, Venturi meter, orifice meter, and pitot tube. Okay, students. So now we will see some of the problems using this Bernoulli's equation. I hope all of you understand this Bernoulli's equation. Okay, Euler's equation and Bernoulli's equation. This is very, very, very important 10-mark question. So if you take any JNTH question paper, definitely in second unit they will ask either problem or this derivation. Okay, so now we will move to two problems today's class. Okay, it's a very simple problem using this Bernoulli's equation. Okay. Okay, students, now we will see the first problem. I will read the question. Please follow. Water is flowing through a pipe of 5 centimeter diameter. So imagine a pipe. Okay, the diameter is 5 centimeter or 50 mm. Okay, under a pressure of 29.43 Newton per centimeter square. So that pressure is called gauge pressure. Okay, and with the mean velocity of 2 meter per second. So in that pipe, the fluid velocity is 2 meter per second. Full stop. Find the total head or total energy per unit weight of the water at a cross section, which is 5 meter above the datum line. 5 meter above the datum line. So the pipe is located 5 meter above the datum line. So what they are asking, total head or total energy. So the total head to total energy is nothing but the Bernoulli's equation. Okay, the summation of pressure head, kinetic head, and potential head. So please see the equation here: P by rho g plus V square by 2g plus Ez. Okay, so now we must calculate one by one. First, P by rho g, pressure head. Okay, what is the pressure P value? It is given in the question, 29.43 Newton per centimeter square. So they're given in centimeter square. So we dealing with in terms of meter square only. So convert this centimeter square into meter square. So if we convert means, please see here, pressure is equal to 29.43 Newton per centimeter square, which is equal to 29.43 into 10 power 4 Newton per meter square. Okay, centimeter square to meter square means multiply by 10 power 4. So P is equal to 29.43 into 10 power 4 divided by rho G. Rho is, so since it is water, what is the density of water? 1000. G is 9.81. Okay, so here we have to multiply. The multiplication symbol is not there. Okay, so 1000 into 9.81. So simplify this equation, we can get 30 meter. So heads always in meter. Okay, next come to kinetic energy, kinetic head. What is the kinetic head formula? V square by 2g. So here we need velocity. What is the velocity? 2 meter per second. So V square, so 2 square. So 2 square is nothing but 2 into 2. So 2 into 9.81. So 2 into G is nothing but 2 into 9.81. So simplify this equation, we get 0.204 meter. Okay. So next come to Z. Z nothing but datum head. Okay. Or potential head. So that is that value is already given in the question. That is 5 meter. We can take directly. Z is equal to 5 meter. So substitute Z equal to 5 meter. So the total head is equal to P by rho G plus V square by 2G plus Z. So the summation of 30 plus 0.204 plus 5 meter, which gives the total head. So that from this equation, the total head is nothing but 35.204 meter. Okay. So just a simple. First write the equation. Bernoulli's equation. That means total head. P by rho G, V square by 2G plus Z. So in this problem, pressure is given. So substitute that value, pressure value. P is over. Next, rho. Rho we already know. 1000. For water, always 1000. Next, G is 9.81. Next, come to velocity. Velocity also given 2. So you can square 2 square divided by 2 into 9.81. Next, come to Z. Z also given in the question 5 meter. Okay. So summation of all this value, we can easily get the answer 35.204 meter. That's all. Now let us see the second problem. A pipe through which water is flowing is having diameter 20 centimeter and 10 centimeter at the cross section 1 and 2 respectively. So in first problem, the pipe is uniform cross section. That means the diameter is same. But in this second problem, the diameter is not same. Okay, you can see the diameter is not same. So the diameter is not same. You can see diameter is 20 centimeter at one section, 10 centimeter at one section. So automatically what happened? Velocity is not constant. At larger cross section, velocity is lower. At smaller cross section, velocity is higher. Okay. The velocity of water at section 1 is 4 meter per second. That means at 20 centimeter diameter. Find the velocity head at section 1 and 2 and also rate of discharge. Rate of discharge is nothing but the rate of flow. So next D1. What is D1? 20 centimeter. If you convert it into meter means 0.2 meter. Next area. We have to calculate the area because here listen here V1 only given, V2 not given. See diameter D1 given, D2 given. V1 given, but V2 not given. So how to calculate? Using the continuity equation. A1 V1 equal to A2 V2. Okay. So for calculating that, we need A1 A2. So A1 is equal to pi by 4 D1 square. So we got 0.0314 meter square. So next come to V1. V1 is 4 meter per second. We already know in the question. You can see in this figure, this is the larger diameter. Here V1. This is the smaller diameter V2. We don't know. That we have to find. So next come to D2. D2 is 10 centimeter or 0.1 meter. So A2, sorry, this is not A1, this is A2. So A2 is pi by 4 into D2 square, which is 0.0785 meter square. Next come to velocity head. So what is the velocity head? V1 square by 2g. First question what they asked, the velocity head at section 1. So velocity at section 1 is V1 square by 2g. So V1 they given in the question. So no problem at all for calculating this velocity head at section 1. So V1 is 4. So 4 square divided by 2g. 2 into, here into symbol is not there. So 2 into 9.81, which gives 0.815 meter. This is the velocity head at section 1. Next, velocity head at section 2 is V2 square by 2g. Now you can see here V2 is not given in the question. Only V1 only they given. So before going to this formula, we must calculate V2. How to calculate V2? Using continuity equation. So A1 V1 equal to A2 V2. So from this A1 we know, B1 we know, A2 we know, B2 only don't know. So B2 is equal to A1 B1 divided by B2. Okay, sorry, this is not B2. This is A2. A1, you can see here A1 B1 divided by A2. So this A2 comes to this denominator. So please make correction. This is A2. Okay. So which is equal to V2 is equal to 16 meter per second. V2 is equal to 16 meter per second. So once you found V2 means velocity head we can easily found. So V2 square by 2g. So 16 into 16. That means 16 square divided by 2 into 9.81, which is equal to 83.047 meter. Okay, that's all. So you can see the question what they asked. Find the velocity head at section 1 and 2. That we found easily. V1 square by 2g is 0.815 meter and velocity head at section 2 is 83.047 meter. So you can see the difference. V1 square by 2g is very, very low. The head is very low. Why? Because the diameter is large. T1 is 20 centimeter. But if you take velocity head, that means V2 square by 2g is compared to V1 square by 2g, it is huge. 83. Here you can see 0.81, but here 83. So why? Because here diameter is very, very small compared to this. This is 20 centimeter and this is half of that 20 centimeter. That means 10 centimeter. So if velocity is velocity is increases means, so here diameter is reduced, not velocity, diameter is reduced. Here 20 centimeter, here 10 centimeter. So velocity is increases. Okay, here you can see velocity is 4 meter here. You can see here only 4 meter, 4.0 meter. But here velocity is 16 meter. That means 4 times more. So according to this, compared to V1 square by 2g, V2 square by 2g is huge. Okay, velocity head is more. What is the second question? Third question they asked, what is the discharge value? So that we already know. Either you can multiply A1 because discharge is same. Okay, A1 B1, or you can multiply A2 B2. You can apply any formula. The Final answer is same. Either you can multiply by A1 B1, that's also correct, or you can multiply by A2 B2, that also correct. Both the answers are same. So therefore Q is equal to 0.1256 meter cube per second. 0.1256 meter cube per second. This is the answer. Okay, so this type of question they will ask 10 marks. Okay, this is very simple question. Once you understand the question, the answer is very small and very easy. Okay, so in this class we discussed what is meant by fluid kinematics, derivation of Euler's equation and assumptions of Euler's equation, and the derivation of Bernoulli's theorem and assumptions and what is meant by Bernoulli's theorem and where it is and applications of the Bernoulli's theorem, and two important problems. Okay, so next class we will see another two important problems in the Bernoulli's equation. So I request all of you attend without fail. Okay, so once if they asking from the Bernoulli's equation, write the formula first. What are the data given? First you analyze the data and what are the data required. Using the formula, you write the datas. Using the datas, we can easily get the required value and substitute, we can get the answer. Simple. Once you understand the question, it is very simple. Okay, students. So we will meet in next class. Thank you.